The Persian Gulf in July does not offer mercy. At 2:28 a.m., the surface temperature is 33 degrees Celsius, and the air above it runs at 81% relative humidity with no wind. A combination that reduces the human body's evaporative cooling to near zero and produces in any enclosed space without forced ventilation a steady accumulation of heat that, in the engineering spaces of a warship, becomes a working environment that the designers never fully accounted for, and the crews manage through experience and endurance. USS Gonzalez makes 17 knots on a northerly heading, 58 nautical miles southeast of Bandar Abbas, escorting a tanker convoy through the Strait of Hormuz approach corridor. She has been at general quarters for 19 minutes since the electronic warfare operator classified the Kish Island radar battery's emission shift at 2:09 a.m. Targeting mode, consistent with a Khalij Fars anti-ship ballistic missile battery. The Khalij Fars launches at 2:14:31 a.m. The intercept geometry is constrained. The terminal approach is near vertical, Mach 3.8, approaching from almost overhead. And the Aegis SM-6 engagement is executed at the tight tolerances that a Khalij Fars demands. The first SM-6 intercepts at 2:15:03 a.m. at an altitude of 11,000 meters. The intercept is effective. The Khalij Fars's guidance section is disabled. The warhead is fragmented by the SM-6's proximity detonation, and the terminal dive phase is disrupted. The second SM-6, fired as insurance 7 seconds after the first, achieves a secondary detonation at 6,000 meters altitude that disperses the remaining fragments. The combined detonation energy of the two SM-6 engagements at 11,000 and 6,000 meters altitude propagates downward as a compound shockwave that reaches the Gonzalez at 2:15:19 a.m. The overpressure at the ship's position, calculated at approximately 0.7 pounds per square inch from the combined near-simultaneous detonations, arrives with the specific character of a shockwave that was generated directly overhead rather than from the horizon. It is a vertical impulse applied to the ship's structure from above rather than from the side. In the aft 5-inch gun mount's ammunition handling system, the vertical impulse arrives at a specific and unfortunately timed moment. The handling system for the 5-inch/62 caliber gun mount uses a magazine below decks at frame 142 to store ready service ammunition, propellant charges, and projectiles staged for rapid loading. The magazine at the time of the shockwave contains 48 fixed ammunition rounds, 5-inch projectiles each mated to their propellant case. The rounds are stored in a rotating magazine drum assembly that cycles them upward through the handling system to the gun mount above. The drum is loaded to capacity for the escort operation. The commanding officer ordered full magazine load before the convoy transit began. A standard defensive posture. The drum assembly is secured by a locking mechanism when not cycling. A spring-loaded detent that engages the drum's circumferential groove and prevents rotation when the gun mount is not in active fire. The locking mechanism is designed to prevent inadvertent drum rotation during ship motion and handling. It is rated for the ship motions expected in normal sea states. It is not rated for 0.7 pounds per square inch vertical shockwave overpressure arriving at 2:15:19 a.m. The shockwave compresses the deck structure above the magazine with sufficient force to momentarily flex the overhead plating of the magazine approximately 4 millimeters. This flex is within the structural steel's elastic range. There is no permanent deformation, no visible damage. But the flex transmits a vertical impulse to the drum assembly through the drum's upper guide bearing. And the combination of the downward shockwave impulse and the spring-loaded detent's resistance produces a momentary cam action that disengages the detent at 2:15:19 a.m. The drum rotates approximately 12 degrees, 1/3 of a round spacing interval, before the detent re-engages. That 12-degree rotation moves the round in the number 3 position down by approximately 8 centimeters and forward by approximately 6 centimeters, enough to contact the round in the number 4 position below it. The contact between the number 3 and number 4 rounds is a low-velocity, low-energy collision. Two 32-kilogram fixed ammunition rounds contacting at approximately 0.4 meters per second. The kinetic energy of the contact is not sufficient to detonate either round. The rounds are designed with significant resistance to detonation from impact, and a 0.4 meter per second contact is far below any credible initiation threshold. But the contact between the propellant case of the number 3 round and the steel retaining ring of the number 4 round produces a small spark from friction between the propellant case's brass plating and the retaining ring's hardened steel surface. The spark contacts the small amount of propellant powder that is sifted from a microfracture in the propellant case of the number 3 round, a fracture that developed during the most recent gun exercise 11 days ago and was assessed as non-structural at that inspection. The powder sifted from the fracture is approximately 0.4 grams, distributed along the bottom of the number 3 round's position in the drum. The 0.4 grams of propellant ignites at 2:15:19 a.m. Single-base propellant powder burning in a confined space does not detonate. Propellant powder is designed to deflagrate, to burn rapidly and produce gas when ignited, not to detonate in the high-order sense. The distinction matters enormously in a magazine context. A detonation of one or more of the 48 rounds in the magazine would produce a catastrophic hull fracturing event from which no DC response is possible. A deflagration, a fire, in the magazine produces a survivable crisis if the DC response is rapid, correct, and executed before the heat from the burning propellant raises the temperature of the adjacent rounds to their own ignition threshold. The ignition temperature of the propellant in the 5-inch fixed ammunition rounds is approximately 143 degrees Celsius at the propellant surface. The magazine at 2:15:19 a.m. is at approximately 41 degrees Celsius ambient, already warm from the Gulf air and the ship's residual heat. The number 3 round's propellant case is in contact with the spark and the 0.4 grams of loose powder that are now burning. The brass propellant case conducts heat from the burning powder to the propellant inside it at a rate dependent on the case wall thickness, 2.1 millimeters of brass, and the temperature differential between the burning surface and the propellant interior. At the current burning rate of the 0.4 grams of loose powder, the case surface temperature will reach 143 degrees Celsius in approximately 4 minutes and 20 seconds if the burning is not interrupted. Adjacent rounds, the number 4 and number 2 rounds, and the number 7 round above the number 3 position, will reach their ignition threshold by conduction and radiation from the burning number 3 case at approximately 6 to 7 minutes after ignition, depending on the magazine's ventilation and the burn rate of the number 3 propellant. 4 minutes and 20 seconds to single-round ignition, 6 to 7 minutes to multi-round ignition. After multi-round ignition in a 48-round magazine, the DC doctrine provides no survivable outcome. The magazine fire alarm activates at 2:15:24 a.m., 5 seconds after ignition, when the heat sensor in the magazine's overhead reaches its threshold from the burning loose powder. DC Central receives the alarm at 2:15:26 a.m. The chief engineer reads it at 2:15:29 a.m., 3 seconds after the alarm arrives. Aft magazine fire, frame 142. He has the suppression options in his head before he finishes reading. The aft magazine at frame 142 has 2 suppression systems available. The first is the magazine water deluge, a seawater spray system designed to cool the magazine by flooding it with water from the fire main. It is fast, effective at temperature reduction, and capable of cooling any number of rounds simultaneously. But water applied directly to propellant-loaded ammunition has a specific secondary effect. The propellant in fixed ammunition rounds is highly hygroscopic. It absorbs moisture aggressively, and exposure to water spray renders the propellant unusable and, more critically, potentially unstable. A magazine of 48 rounds that has been flooded with the water deluge is a magazine of 48 rounds that cannot be fired, must be completely unloaded under controlled conditions at a naval ordnance facility, and may have propellant stability issues that require individual round assessment. This is not a trivial outcome for an escort ship in the middle of a convoy defense operation. The gun mount is offline until the magazine is emptied and restocked. The second is the magazine CO2 suppression system, a fixed CO2 installation that floods the magazine space with carbon dioxide at a concentration sufficient to suppress any combustion by displacing the oxygen. CO2 applied to a magazine fire does not damage the propellant, does not affect round serviceability, and does not require post-activation unloading and inspection of the unaffected rounds. If the CO2 suppression is effective, the magazine's 48 rounds remain fully serviceable, and the gun mount returns to operational status following ventilation of the CO2 atmosphere. The magazine's CO2 suppression system is the correct choice if it will work. It works if it has adequate supply pressure and if it achieves suppression concentration before the number 3 rounds propellant case reaches 143 degrees Celsius. The CO2 supply for the magazine suppression system draws from the ship's main CO2 bank, a manifold-connected bank of CO2 cylinders in the CO2 storage room at frame 98. The same manifold also serves the main engine room's CO2 suppression system, which is the fixed system that would be activated in the event of a fuel fire or other major thermal event in the engineering spaces. The two systems, magazine suppression and engine room suppression, share the main CO2 bank through a manifold with dedicated branches to each. The manifold is designed to allow independent activation of either branch. The CO2 bank contains a total charge of 280 kilograms of CO2. The magazine at frame 142 requires approximately 45 kilograms of CO2 to achieve suppression concentration. The main engine room requires approximately 160 kilograms of CO2 for a full suppression event. Total bank, 280 kilograms. Magazine requirement, 45 kilograms. Engine room requirement, 160 kilograms. Sequential use of the bank for both systems is feasible. The magazine suppression leaves 235 kilograms available for the engine room, well above the engine room's 160 kilogram requirement. But simultaneous activation of both branches would deplete the bank faster and reduce the available pressure at each branch, potentially leaving either or both systems short of the required concentration. The systems are designed for sequential use, not simultaneous use. This is not a theoretical concern. It is a specific operating limitation that the chief engineer is aware of because he has read the CO2 system documentation. The main engine room, at 2:15:29 a.m., does not have a fire. There is no alarm for the engine room. The engine room watch is at their station and has reported no anomalies. There is no immediate reason to activate the engine room CO2 suppression system. But the shockwave that tripped the magazine drum detent at 2:15:19 a.m. also passed through every other space in the ship with the same 0.7 psi vertical impulse. The chief engineer does not know whether any other system in the ship has experienced a similar secondary effect. A component at its tolerance margin, pushed past it by the shockwave, beginning a failure sequence that is not yet visible. The engine room has a JP5 fuel manifold that runs adjacent to the aft engine room's starboard bulkhead. He has not received an engine room alarm. He has not received a fuel leak indication. He cannot know that the engine room is definitively safe for the next 4 minutes and 20 seconds while he uses the CO2 bank on the magazine. He can know that it does not currently have an alarm. He can know that the magazine has an alarm and a 4-minute and 20-second window. He can know that the sequential use of the CO2 bank leaves 235 kilograms for the engine room if needed. he activates the magazine's CO2 suppression system at 2:15:33 a.m. 4 seconds after reading the alarm, the CO2 discharge into the magazine at frame 142 begins at 2:15:35 a.m. The system is designed to achieve suppression concentration in approximately 25 seconds of continuous discharge. The magazine atmosphere transitions from the 21% oxygen of normal air to the sub-15% oxygen concentration required for fire suppression by approximately 2:16 a.m. The burning loose powder in the number 3 round position is suppressed at 2:16:04 a.m. The heat sensor in the magazine overhead begins showing a temperature decline at 2:16:09 a.m. as the CO2 atmosphere absorbs heat from the burning surface and the deck structure. The magazine fire is out at 2:16:04 a.m., 45 seconds after ignition. The temperature of the number 3 rounds propellant case at the moment of suppression is assessed by the magazine's thermal sensor array at approximately 68 degrees Celsius, well below the 143-degree ignition threshold for the propellant interior. The adjacent rounds, numbers 2, 4, and 7, show temperatures between 44 and 51 degrees Celsius, which is elevated from the ambient but represents no ignition risk. The magazine is now filled with CO2 at suppression concentration, approximately 34% CO2 by volume. No personnel can enter until the CO2 is ventilated and the atmosphere is confirmed safe for entry. The ventilation procedure for the magazine after CO2 activation requires opening the magazine ventilation valve, allowing the CO2 to clear over approximately 15 minutes, and then checking the atmosphere with a CO2 monitor before any entry. The CO2 bank has discharged approximately 47 kilograms into the magazine. The full suppression dose, plus a small overpressure charge to ensure full concentration, remaining in the bank approximately 233 kilograms. The engine room suppression system has its 160 kilogram requirement available with 73 kilograms of reserve. The bank is adequate for the engine room if needed. The engine room does not develop a fire. At 2:16:41 a.m., the engineering watch reports the engine room is normal. No fuel leak, no heat anomaly, no damage from the shockwave. The fuel manifold inspection at 2:18 a.m. confirms no evidence of fitting displacement or seal disruption from the shockwave. The engine room was not at risk. The sequential use of the CO2 bank was the correct choice, and it left adequate reserve. The magazine ventilation is complete at 2:31 a.m. The magazine atmosphere is confirmed safe for entry by CO2 monitor at 2:31 and 12 seconds a.m. The gunner's mate and the magazine watch enter the magazine at 2:31:19 a.m. in accordance with post-suppression entry procedures. Their assessment: the number 3 round shows visible propellant case discoloration at the contact area, a heat stain across approximately 12 centimeters of the case lower surface where the loose powder burned. The round is non-serviceable and is tagged for removal and ordnance inspection. The adjacent rounds, numbers 2, 4, and 7, show no visible heat damage. The remaining 44 rounds are assessed as serviceable pending a formal ordnance survey. The drum assembly is inspected at 2:34 a.m. The detent mechanism is examined. The spring-loaded detent shows no permanent deformation, no mechanical damage. The shockwave's vertical impulse momentarily overcame the detent's spring force, a force of approximately 18 kilograms, by producing a transient compression load on the drum's upper guide bearing, during that generated a cam action against the detent. The detent is functional. The drum is functional. The mechanism that allowed the drum to rotate 12 degrees under the shockwave load is a design characteristic, not a defect. The detent is designed to prevent rotation from ship motion, not from a 0.7 psv vertical shockwave. The magazine is declared serviceable with 44 of 48 original rounds at 2:41 a.m. The gun mount is brought back to operational status at 2:43 a.m. 44 rounds in the ready magazine. The convoy escort continues. The post-event debrief considered 2 questions. The first was whether the decision to use CO2 rather than water deluge was the correct call given the uncertainty about the engine room. The chief engineer said yes. He said the CO2 bank has 280 kilograms. The magazine requires 45. The engine room requires 160. And the sequential total is 205. 75 kilograms of reserve in the bank after both sequential uses. He said the bank was designed with this architecture specifically to allow magazine suppression without compromising engine room capability. He said, using the water deluge, the operationally more conservative choice that preserves the CO2 bank entirely, would have rendered 44 serviceable rounds non-serviceable and taken the gun mount offline for the convoy operation. He said the CO2 system exists so that outcome is not necessary. The second question was whether he considered the engine room risk before activating the CO2. He said yes in the 4 seconds between reading the alarm and activating the system. He said the engine room had no alarm, the engineering watch was at station, and the JP5 fuel manifold had not shown any indication of disruption. He said his assessment was that the engine room was not on fire and was unlikely to develop a fire in the next 4 minutes. He said he acknowledged that he could not be certain. He said the magazine had a confirmed fire and a 4-minute and 20-second window. He said certainty is not always available. Probability is. 1 Khalij Fars intercepted by 2 SM-6 missiles at 11,000 and 6,000 meters altitude at 2:15:03 and 2:15:10 a.m. Compound shockwave overpressure at Gonzalez, 0.7 pounds per square inch. Aft magazine drum detent disengaged. Drum rotated 12 degrees. Round-to-round contact in magazine drum. Propellant powder ignition at 2:15:19 a.m. Magazine fire alarm activated at 2:15:24 a.m. CO2 suppression authorized at 2:15:33 a.m., 14 seconds after ignition. CO2 discharge at 2:15:35 a.m. Fire suppressed at 2:16:04 a.m., 45 seconds after ignition. Number 3 round propellant case peak temperature, 68 degrees Celsius, below 143 degree ignition threshold. CO2 bank discharged, 47 kilograms of 280 available. Remaining for engine room, 233 kilograms, adequate. Magazine ventilated and safe for entry at 2:31:12 a.m. Magazine serviceable at 2:41 a.m. with 44 of 48 rounds. Gun mount operational at 2:43 a.m. Ship status operational. The number 3 round. The round whose propellant case fractured 11 days earlier at a gun exercise, whose microfracture allowed 0.4 grams of powder to sift to the base of its magazine position, whose brass case met a hardened steel retaining ring at 0.4 meters per second and produced a spark in the Persian Gulf at 2:15:19 a.m. is in the Ordnance Disposition Yard at Bahrain. The inspection confirmed the fracture origin at the exercise. A stress riser at the case crimp, consistent with a loading that exceeded the case material's fatigue limit at that geometry. The fracture was within the visual inspection tolerance when it was observed 11 days ago. The 0.4 grams of powder it released was below the mass that the post-exercise inspection protocol requires to trigger a round removal order. The inspection tolerance and the protocol were both within their designed parameters. They were also both present in the magazine at 2:15:19 a.m. when the drum rotated 12 degrees. The chief engineer's recommendation in the post-event report was not to change the inspection tolerance. He said the inspection tolerance is appropriate for the failure mode it is designed to catch. He said what happened was a compound event. A propellant case fracture with intolerance, plus a drum rotation event outside the drum's design loading envelope. And that compound events of this character require compound responses. He recommended two things: a post-shockwave inspection protocol for ammunition handling systems after any engagement-adjacent shockwave event, and a reduced drum load level for ready service magazines during active engagement conditions, reducing the drum to 32 of 48 positions to provide separation between adjacent rounds and reduce the kinetic energy available from a contact event. Both recommendations were accepted. The post-shockwave inspection protocol was implemented within 60 days. The reduced drum load level for active engagement conditions was implemented within 90 days. The magazine at frame 142 on USS Gonzalez now has a placard above the drum load control that reads, "Active engagement. Load to 32 rounds maximum." It has been there for 7 months. No one has had to use it yet.